we can dive into lecture 2. How would that be? I have lots of fun pictures for you in lecture 2. My husband was afraid I was going to scare you. So I'm just going to tell you, I'm not showing these to scare you. I just want to show you pictures of what it looks like when these variables, what these sort of variables would look like, right? You've learned the names, and now you can learn sort of the pictures that go with the names. That was my goal here. So, lecture 2. Let's start this one up. So, univariate data description. That's what we're going for here. Gesundheit. Univariate meaning one variable at a time. So you will have heard of all of this if you remember anything from intro stats or research methods, but in case you don't remember, I'm going to tell you again. So univariately, it turns out that when we have categorical variables, this task is easy. Describing a categorical variable by itself, you just have to tell how many are in each category. The end, right? You can report that as a frequency or a percent, but that's it. Describing a quantitative variable is more in-depth because there are at least 3 things that we want to be able to convey, possibly 4 depending on who you ask. So as a side note here, when we're thinking about these quantitative variables as predictors, really the only thing that matters is this categorical versus quantitative distinction. When we're thinking about these variables as outcomes, then the more fine-grained distinctions of binomial, count, continuous, and that sort of thing matters. Because the model has to understand when it needs to shut off and when it doesn't. So first up, let me give you an example here. How many of you know what a mean is? Hooray, we got it all, right? So let's, how many of you are parents? Let's do this. Several of us, okay. So if I told you that the mean age of my kids is 8, you're like, okay, that doesn't tell me much about your family, but the mean age is 8. What if I told you that I had a stepdaughter who's 12 and a son who's 4? That's a different picture that comes to mind than if I told you that I had a 7-year-old and a 9-year-old. Right? My life is different because of the spread. Right? So this concept shows up right away in quantitative variables. Central tendency, the mean being the most obvious example. Turns out there's more than one kind of average. So I'm being more specific here, the arithmetic average. Median, you've probably heard of that one. Middle value, yeah. Mode, most frequent value. Almost everything we're going to focus on is mean. The others are just sort of here descriptively. But the other part, the spread, that's related to a concept called dispersion, the width of the distribution. So how far away are the quantitative values from each other? That's what we want to be able to characterize. The average awayness, so this is a new word here, deviation. The average deviation from the mean has a special term, it's called the standard deviation. Standard deviation squared is something called variance. Variance, think variability. It's the sum total of all, basically it's the squared offnesses. You can think of it as just like, I have all this stuff, like what's the total spread? Variance is a concept more than a number. If you have data that are not well described by these things, put a pin in that, come back to it, there's something else that shows up under this category called interquartile range, which is another way of characterizing dispersion. So to motivate the third one, let me continue with my example. What if I am not just someone with 2 kids, or 1.5 kids, as I sort of say, because my stepdaughter's only here sometimes. What if I said that I had like 3 children under 5 and a 10-year-old? Oh, like the average age of that might be somewhere around like 6, but that does not describe the horror it would be to have 3 children under 5, right? Does anyone have that? No. Yeah, I can't even keep up with what I have. I can't even imagine, right? So what we're talking about here is the asymmetry of the distribution, right? Skewness is the term. In that example, the ages are skewed to the younger side. So I got to know that beyond just the mean, beyond just how far off from the mean, Are all the oftenesses concentrated on one side versus the other? That's skewness. There's a fourth one that shows up, kurtosis, but we can ignore that for right now because we don't ever do anything about that. So the variables that we have each come with their own flavor of something that's called a distribution. More formally, probability distribution functions. Each one of these is a formula. It's a formula someone else figured out. Remember, we're trusting the people who figured this out. We're not going to second guess them and derive them like they know what they're doing. Cool. It's a formula that produces a value. What we use this for is that given certain salient features, such as the mean, the variance, the distribution function gives us the probability or the likelihood of observing any value for our variable. So that's useful. Which one depends on the type of variable that it is. And so this is where we have, in terms of distribution functions, we have discrete versus continuous. Discrete means integers only. Continuous means it can go in between. And so from a math perspective, this matters a lot more. From a modeling perspective, we tend to sort of swap them out. Like I might, even though a count is discrete, I might try to fit it with something that's continuous. This is where he's like, they're going to lose their minds. But no, I just want to show you pictures, okay? Pictures, that's it. I give you the distribution functions because some of you are going to need to know them looking at you guys, quant people. Okay, and she's like, I got this. I was a math major. I'm not afraid of this. I was afraid of this. So, yeah. In the pictures that are coming, the x-axis shows the possible values of the variable. The y-axis shows the likelihood of observing each. Likelihood, think probability. How frequently we would observe each, given the properties of the distribution. So there are mean, variance, and skewness. Those are the things that we have to know what the shape of the distribution looks like. And I have in here, this is how they get used. It's like if your outcome follows the blah blah distribution, then the parameters of that distribution, characteristics of the population, provide its mean, variance, and skewness. So you know that, you know what the shape's supposed to look like, according to these formulae. So here's one. This is the easiest one. This is for binary variables. Remember what binary means? Either or, right? Easy. That follows something called the Bernoulli distribution. So here are 3 examples. If I have a situation in which 75% of my cases, the blue bar here, have a 0, how many percent have a 1? 25. If it's 50% 0, how many have a 1? 50%. Yeah. And I know the answer's right here, but if you know that the whole is 100%, and you know one of them is the other one, you can figure out the other, right? It's determined. It's given. So that is to foreshadow this parameter has only one, this distribution has one parameter. It's called P. It's the proportion of ones. Once you know that, you know how many zeros there are. So the mean is P, and the variance is a function of the mean. So when you have 50-50, that's as much variability as you can possibly have. So if this were an outcome, this is the type of distribution that we would use. The only thing we would have to find is P, and we would find it as a function of each distinct type of predictor in the model. If I have more than 2 categories, here's an example of a multinomial distribution. If I have 3 categories, I have 2 P's. If I know that the first outcome possibility was 50% and I know the second was 35, then because these have to sum to 1, I know what the third is. So there's 2 parameters that give me frequencies. The third is determined, and that will always be the case that you need 1 fewer. So why does this matter, how many categories you are? Because I want to foreshadow what happens when we think about these variables as predictors. So for a binary variable, for instance, only 2 options, when we put that variable in the model, all we need to do is put the original variable in. That's it. So binary variables are usually coded 0 versus 1. That's it. We put that in, and we find out how much more likely something is to happen if you're a 1 instead of a 0. Cool. But if we have a categorical predictor with more than 2 categories, we can't just put that in as one thing, because there's not just one p that gives us the percentage in each category. There's number of categories minus 1. So in the previous slide, for instance, let me go back, there's 3 possibilities. In order to differentiate 1 versus 2 and 1 versus 3, that's 2 different things I need. 2 predictors. Now I can go any way I want. I could say I want 1 versus 2 and 2 versus 3, or I could do 1 versus 2 and 1 versus 3. But either way, I need to know 2 things in order to figure this out. It's 2 terms that go into the model as a predictor. So this is just foreshadowing how people would approach this. For instance, if I have a variable that has 3 categories, whether they're in a control group, the first kind of treatment group, or the second kind of treatment group. A classic approach to putting this type of variable in the model would look like what it is on the left here, where we make new ones. We take my original variable, where 0 is control, 1 is treatment 1, and 2 is treatment 2, and we recode it into 2 new variables. So when we put these in the model together, if I give the control group a 0 in both places, I give treatment 1 a 1 here, and I give treatment 2 a 1 here. What these contrasts, these 0 versus 1 information, end up giving us is the difference between treatment 1 versus control here, and treatment 2 versus control there. That's what's known as dummy coding. And that's not meant to be like a pejorative term, like that's what it's called. It's dummy coding. In contrast, here's a different way of looking at it. Still 2 things to be able to figure out what the proportion is in each of the 3 categories, but doing it differently. This is a coding scheme that would allow me to answer, is there any kind of effective treatment at all? And that's lumping together the 2 treatment types and contrasting them with control. The second term then splits apart the 2 treatment types. Within treatments, is 2 versus 1 any different? So again, this is foreshadowing what's going to happen to these variables in a model. But the big picture is that you need C minus 1 new predictors to be able to differentiate all C categories. So if I have 3 categories, that's 2 predictors. If I have 4 categories, that's 3. Yes, you got it. And if I have 2 and it's binary, I only need 1. Ta-da. You can always figure out the missing one, the missing comparisons, because it's determined once you have those C minus 1 in there. All right, more pictures. Binomial. So this is 3 different binomial distributions. Let's say that I have a test with 20 items. So I'm modeling the number of correct responses. If I have a probability of 0.1, that gives me this distribution. Most of the people are down here on the low end. It's very unlikely that you'd have very many correct responses if the probability of getting any one correct is only 10%. The opposite, on the green one, that's an easy test. If the probability of getting any one item is 0.9, then we have a lot of people who are at the end, and not as many down here. So what makes this distribution special is that it understands that even if the probability goes all the way to the end, you can't go past the boundaries. It will keep it within 0 and the number possible. So that's why I say this corresponds to things like rates and accuracies, because you can always go from number possible to percentage out of 0 for 100. Now look at the red one here. The red one's sort of special. That's when the probability of getting a correct answer is 50-50. It's not lopsided anymore, right? It's symmetric. So for variables in which this is what it looks like, a lot of people would be tempted to treat that as something that is sort of continuous because it doesn't appear to hit the boundaries. But once we know the probability of a 1, this distribution tells us what the mean is, what the variance is, and what the skewness should be. And skewness, this asymmetry, is a direct result of hitting the boundaries. You can't go past a certain point, so the data have to be skewed. More pictures. Almost done, I swear. Poisson. Does anybody speak French here?
Oh, but I know it means fish.
It does. And I have no idea if that has anything to do with this. I just happen to know that. I don't speak French. I speak a little bit of Spanish, but that's it. So this one is for counts. And yeah, just, pay no attention to all of that. That's just, you put the stuff in and a number comes out. That's all you need to know. This one also has only one parameter for the mean because the mean is supposed to be the same thing as the variance. So this is the type of distribution you would get for counts, something that doesn't happen very often, like number of times a kid gets sent to the principal's office, something like that. That would be the yellow one. If most kids don't get sent, and if you do, that would create a distribution that's like up against the wall here, right? Because you can't have negative times going to the principal's office. Most people are to 0, and it's kind of like skewed that way. The purple one would be an average of 4, still skewed because it can't go as far to the left as it wants to go to the right. And the blue one is an expected number, a mean of 10. That one doesn't look skewed anymore. So once you move off the wall enough, you start to see these things look symmetric. And those are the situations in which you can borrow symmetric distributions to use it. This is a stretchy Poisson. Let's all call it that. It's called negative binomial. There's another one, has extra skewness to it. And this one is called zero-inflated. So you see this a lot in situations in which the population you're studying is both qualitatively different and quantitatively different. So let me give you an example. A variable something like severity of childhood sexual abuse. Hopefully, you have a huge pile of people who answer 0, right? No severity, because nothing ever happened to me. But for the people who unfortunately did have something happen to them, they vary more continuously in severity. So a distribution that looks like this arises from combining 2 different kinds of people. People who they don't have the phenomenon applied to them, and people who do to some extent. In this example, this is from a journal article looking at steps taken towards divorce, for instance. So there's 2 kinds of people in this pile of zeros right here. There's people like, steps taken towards divorce, I love my partner, I would never do that, 0. Or, I'm gonna, I just haven't gotten around to it yet. Steps taken. So this is what's known as zero-inflated. If this population was only people who were planning on getting divorced, you would only expect a certain amount of zeros here. But because there's this extra type of person in here, that's the logic by which we have this extra. So it's zero-inflated. There are distributions that work for that, and there's 4 overlaid here trying to demonstrate what the differences are. What I'm going to end up doing in practice with these sorts of predictors is literally making them into 2 variables that I'm going to call if and how much. So you take this type of variable, and the first step is to divide out the people who have a 0 versus the people who have anything else. That's the if group. That's one effect. What is the effect of having anything past 0? Like any kind of abuse whatsoever, right? People who have no abuse versus some abuse. Then just in the people that are above 0, how bad was it? If and how much? That helps to answer questions about whether or not it's experiencing anything that's the problem versus the severity. So that also works for things like drug use, right? Like is any marijuana cigarette bad for you, or is it bad to have one every day? I don't know, right? It depends on the context. So there's a lot of, I think, examples in social sciences that fit this sort of thing, which is why I wanted to show it to you. So, do any of you have any of those from your worlds? This if and how much sort of, no? No? Okay, that's fine. You're like, yeah, I'm not talking because we're almost done and maybe she'll let us go. Yeah, I think that's a good place to stop. So the common denominator of all the previous plots here, these are all for discrete variables. So these categorical, where the variable numbers are labels. Binomial, where it's the number correct, or number of events out of sum total, which you can convert to a rate if you want to. Poisson, where it's the count of things that happened, and you can't have counts that are negative or in between numbers, non-integers. And zero-inflated versions of that. The other ones then are where we get into stuff that's truly continuous. And that's where we get to your new best friend, the normal distribution. Sure you've heard of that, right? Yeah. It's a way of life. We're going to meet it next time and get to know it very well. Good? All right, questions before we adjourn? Yes? Yes.
The data was like this, like everywhere, skewed.
Like skewed to the left and skewed to the right? That would be called bimodal.
It would be same as like this.
Here, are you saying draw like something where it's like that and that?
Yeah, that one and
Flipping it upside
Oh.
as well.
Well, that's like my best no skewness, right?
and then in terms of skewness, the two data have the same.
I'm sorry, I'm not following you.
In terms of skewness, the two data
Oh,
have the same.
the same value?
And on the top, they're the two sides, they're
Mhm.
equal in their skews.
Oh.
That's- If two sides are showing equal amounts of.
Gotcha. I would not call this skewed. I would call this bimodal. But if it's, the question would be like whether they have the extra, like if they have the room to do that. So if you have something that's bimodal because you have people who are really bad at something and really good at something, if your test can only go so far, you're not going to be able to see the other half of this. But I'd still call it bimodal in that case. Skewed is really about asymmetry. That's bimodal, that's skewed. Okay. Sorry, apparently I should have went with the Mountain Dew today, but I already had 2 coffees, so he's like, yeah, you should have. All right. Other questions? All right. Have a good weekend. I will let you know when your quiz is ready on Icon. Watch Beat Shazam on Monday night if it's on.